Okay, welcome to lecture. We'll get started here in just a sec. And again, make sure you put the here in the chat there for all. And we're continuing on in chapter 12 here, I think, on kinetics. Okay, so we've been talking about kinetics, and we talked about last time a couple of things, mainly how to sort of calculate the rate law. Remember that when we do the rate law, it is based solely on just the reactants. So just the reactants are involved in that rate law. And again, the rate law kind of like upper right here on the slide, where we have the rate is equal to K, which again is the rate constant, and that's a lowercase k. And times the concentration of just the reactants, again, to either X or Y, which is what is referred to as the orders for those reactants. And again, those things are found experimentally, as we talked about last time, which means you typically will get that table, like we did a number of examples. And in that table, you'll have various concentrations of your reactants. You'll also have the initial rates of your reactants, and doing sort of that calculation, which is usually the best approach, where you find two entries in the table where the concentrations of one of the reactants, for example, remains the same and the other one varies, and kind of do the rate 2 over rate 1. And again, at that point, what you're able to do using that sort of data information is to figure out the individual orders for each of the reactants. If there happens to be more than one, obviously. And that will allow you to find the completed rate law. And as we saw in a number of those examples, once you sort of find the completed rate law, you then can use that same information in the table. And it doesn't matter which entry that you choose from the table, but you can use that information to calculate the actual value of the rate constant. And we sort of touched upon it last time as well. And again, here, as we're getting into this, that the units that are associated with the rate constant, or that lowercase k, is really important, because it does really tell you sort of the overall order of the reaction, which can be found by adding up the exponents there for each of the individual reactants, but just by the units that you see associated with that rate constant. Then towards the end here, we got into first order reactions and sort of more specific type of reactions. And again, the first order reaction, as we sort of see here on the screen, is typically when we have one reactant that goes to the product, and the order for that one reactant, for example here, A, was to the first order, which means overall the reaction here is first order. And when we look at the rate law for that, the rate is equal to K times concentration of A. And really what that means, sort of a first order reaction, is that the rate itself for that particular reaction, it is dependent on the concentration of the reactant, as you can see there. So just, you know, if you just want to cut out all the other stuff and just kind of think about it mathematically here, if I wanted to calculate the rate and I had to put numbers in here, if I varied the concentration of A, either up or down, it will have an overall effect on the actual rate of the reaction. So that's sort of what the first order overall reaction sort of represents, is that this particular reaction, the rate of it is dependent on the concentration of the reactant in this case, which is A. And again, like I said, obviously here, since we're multiplying basically K times A, if I increase the concentration of A, just mathematically speaking, A went up, the rate value should go up, and vice versa, right? If I lower the concentration of A, it should go down the rate, right? Because A would be a smaller number, and K times a smaller number will give you a smaller rate. So if you just want to think about mathematically, you know, that's sort of what's going on here. If we do rearrange the rate law here and solve for K, and just kind of do the units, which is what we got going on over here that we talked about last time, this is what we typically see for the units here for a first order reaction when we look at the rate constant. And the rate constant unit there are 1 over seconds, or reciprocal seconds. which are the typical units that we associate, again, with a first order reaction. So as I mentioned, as you go through some of these problems, some other problems as well, they won't always necessarily kind of in flashing lights say, hey, this is a first order reaction. They may just give you the rate constant and the units there, and they would assume that by seeing the units associated with it, you'd be able to determine that it is a first order reaction. Now, when we talk about 1/seconds, as I think mentioned last time, it doesn't always have to be seconds, but it is really 1 over a unit of time. Again, it could be minutes, it could be hours, you know, it could be days. But usually seconds is a very common unit, as we talked about last time, because again, when we do typically run experiments, you know, they don't typically run for days and days and days. You know, so a lot of times experiments run very quickly, you know, within minutes or whatever, or seconds. So 1/seconds, again, is a very common unit that is used. Now, when we look at these graphs here, there are two sort of graphs associated with a first order reaction. The one on the left there is on the Y, we have the concentration of A versus T, which again here is time. And as we see here, what we would expect is, since this is a one-way sort of reaction, we do see that over time, we do see this decrease happening in the concentration of A, which is what we typically would expect. Now, definitely with kinetics, we definitely have a lot of graphing that happens, and we definitely like to kind of relate things in the form of a straight line. And that's where our y equals mx plus b comes into play. And we actually get sort of this graph over here on the right by using this equation. And this equation, again, is something that you do need to know, and it is specific for a first order reaction. And that's the natural log of A equals the natural log of A naught minus KT. And as we talked about last time, the natural log of A, the A by itself there on the left, is sort of like your final concentration, if you want to think about it. The natural log of A naught, the A naught with the little circle on the bottom, that's what the little naught is the initial concentration. K is the rate constant, and T is time. And we could use this sort of equation here in a first order reaction to determine how the concentrations are changing with time. We could also figure out how much time it would take for a concentration to change. So you could solve for any of those sort of things in that equation. And we'll see it here in a second on another slide, but at the end there, I also put up another equation that's associated with first order reaction, which is the half-life equation. And the half-life is equal to the natural log of 2 over K, again, K being the rate constant. Natural log of 2, again, on your calculator, if you punch it in, is 0.693, so that's where that number comes from. And oftentimes, you may have to use the half-life equation and that integrated rate law sort of together. But coming back to sort of the graph here, if we rearrange that integrated rate law in the form of a straight line, which is what we have up here that we did, that we get the natural log of A is equal to minus KT plus the natural log of A naught. And what that means is we get the typical plot that we look at for a first order, which is the natural log of A on the Y, T on the X. And what that will yield you is, as you can see here, a straight line. And you'll get a straight line with a negative slope. And the slope of that line will equal minus K. And because the line is actually a negative slope, when you calculate the slope value, you will get a negative number. The negative and the negative will turn your K value into a positive number, which it should be. And again, that's why it's equal to the slope's not equal to K, but it's equal to minus K. Again, that will turn that number into a positive value. So in terms of first order, as we sort of talked about last time, important things on this graph or this table here, or this slide, whatever you want to call it, again, is the stuff with the asterisks, I think, from last time. It is the integrated rate law, the half-life equation, the units associated with it, and again, the two graphs. And I'll be honest with you, out of these two graphs, usually most people, when we talk about sort of the graph for first order, it is definitely the one on the right here. That straight line graph is always sort of the graph that we sort of look at. And when we plot graphs doing kinetics, we always try to do that best fit straight line type of graph. Any questions on any of the stuff we talked about last time?
I have a question.
Yeah.
So there's the rate law and the integrated rate law. So like on a question, for example, would we know which one to use, or how do we like determine which law to use?
Yes. So, believe it or not, it's usually pretty easy to sort of determine sort of which one to go with. In most cases, if you're given a table of information, kind of like the previous examples we did, then you probably would be looking to solve for the actual rate law. And probably, I would say 9 times out of 10, that's probably the place where you would use the actual rate law, believe it or not, is in a problem where you would actually be asked to solve for the rate law. When you're given a problem where they start to give you actual concentrations, they give you some time information, that's when you want to kind of default to this one here, which is sort of your time and concentration one. So it'll be pretty clear as to sort of which one to use. And like I said, usually if it's some type of problem like some of the ones we're going to come up upon here in a second, where you got some concentrations given to you and you got some time, they're like, you know, what is the concentration after 500 minutes or something like that, then it's definitely that integrated rate law where you have to do concentration and time. And again, usually there's probably not a heck of a lot of problems where oddly you kind of take this equation, you plug numbers in. There can be, but most of the time, if you're looking for that real rate law there, it's usually in relationship to a problem where you're trying to solve for what the actual rate law is.
Okay.
Yep.
Thank you.
You're welcome. Other questions? Okay. So let's see here. So again, this is a graph of sort of a first order reaction. And again, pretty much all graphing, there's a lot of graphing that is done here in kinetics. And again, you get a lot of sort of experimental information that you need to do this. And again, this is basically our y is equal to mx plus b. We can see what we got graphed here is the natural log of our reactant. So this is again in that form of the natural log of A is equal to minus kt plus the natural log of A naught. And again, that is our y is equal to mx plus b. So again, we see on the y what was graphed was the natural log of our reactant. On the x is our not temperature, our time. And again, you can see it gives us a nice straight line here. And as you can see here, if you take delta y, the change in the rise over the change in the run, that is equal to the slope, right? And in this case, the slope would equal minus k. So if we actually did calculate that, and again, this is how you would do it. You have a couple of points. And typically when you do calculate the slope of a line, if you happen to graph it yourself by hand, you typically want to take 2 points that are actually, as you can see here, on the actual line, not actual points that may be off of the line or anything like that, and usually not at the extremes there. And again, this would be like x1, y1, and like x2, y2. And again, you could calculate the slope that way. And again, when you get that, it will really equal the rate constant. Again, it will give you a negative number, and that negative and negative will turn it into a positive number. So why don't you try this example here. The reaction 2A goes to B is first order with a rate constant of 2.8 times 10 to the minus 2 at 80 degrees Celsius. How long will it take to decrease the concentration of A from 0.88 to 0.14? So why don't you take a couple minutes and then we'll talk about it. Okay, so let's take a look and kind of see what we got going on in this particular one. So remember that, a lot of good pieces of information does come from the problems. So first off, it does tell us it is first order, which is important since it really only has one reactant and it's first order with A. We know that the rate law, if we needed it, which we actually don't in this particular one here, would technically be something like this. In addition, if by some chance they did not tell us that it was first order and they just kind of gave us the rate constant, the important part here would be when we look at the rate constant, we do see that the units here for K is reciprocal seconds. And that right there, without them telling us, allows us to know that it is a first order reaction. And why that's important is at this point, we actually only know some formulas for a first order reaction, but very soon here we're going to see some for second order, zero order as well. And what this tells us is because this is a first order reaction, we do really want to use the integrated rate law here for our first order. And that's because, we're interested in how a concentration is changing with time. So we got some concentrations given to us, kind of like the earlier question was asked. We're looking for really time, how long it's going to take. So again, concentration is time. We're not going to use this really. We do want to use this because this is, again, the equation that we use when we're trying to figure out sort of that relationship, time and concentration in a sort of first order reaction. So we have a couple of numbers given to us. We have 0.88 molar. That's actually our initial concentration. And we have 0.14 molar, which would be our final concentration. So if you're just kind of ticking off what we got this guy, we got this guy, and we got this guy, which means we can solve for T. So we just want to plug it in. So the natural log of our final here, which again is this guy, 0.14 equals the natural log of our initial 0.88 minus our rate constant, which is 2.8 times 10 to the minus 2 reciprocal seconds, and our time, which is what we're looking for. So there's a couple of ways you could kind of do this mathematically. I personally would take my calculator and go the natural log of 0.14 and hit equals. And then essentially what I want to do mathematically is subtract this guy to the other side. So I would take basically the natural log of 0.14 and then subtract it from the natural log of 0.88. Again, that would cancel out on that side. So I'm going to do that natural log of 0.14 minus the natural log of 0.88. And that's going to give me something like minus 2.84611. Take it out to a couple digits. Minus equals minus 2.8 times 10 to the minus 2 reciprocal seconds times T. At this point, we need to divide both sides by this guy. And bring that over here. Again, negatives and negatives are going to cancel each other out. And if we do that, so we're going to take that number divided by 2.8 to the minus 2. And try that again here. Natural log of 0.14 minus the natural log of 0.88. I'm sorry, I think I wrote the wrong answer there. Here. Try that again. All right, one more time with meaning here. Natural log of 0.14 minus the natural log of 0.88. Helps if you hit the right number there. That is actually 1.83827. Now divided by 2.8 to the minus 2 gives me roughly time is equal to, we'll call it 66 seconds in this case. The units of seconds are here. It's 1 over seconds. When we divide it to the other side, the seconds come up on top. We get about 66 seconds in this particular case. Any questions on any of those steps there? So again, that's probably the easiest way to do it. Natural log of 0.14, and then subtract to the other side the natural log of 0.88, and then divide by negative 2.8 times 10 to the minus 2. And again, you get 66 seconds. Really, the units that are left over at this point are here, or just the seconds. You may be asking sort of, you know, what happened to the molarity units, because we're kind of technically doing this move. Natural log of that minus the natural log of 0.88 molar. You may wonder, isn't the molarity unit still there? And they're actually not, because mathematically speaking, if you do something like that, that's the same as taking basically those two numbers and dividing them mathematically. And that's how technically the molarity goes away. So that's sort of a mathematical operation where you could factor out the natural log from both of these and divide them. And again, that's how the units of molarity actually go away. If you're curious, you know, where the molarity went is technically when we did that subtraction part, mathematically speaking, it's the same as dividing those two numbers and factoring out the natural log. And again, that's how the molarity actually goes away. Any questions on that?
Professor?
Yeah. Yeah.
Do you think you can explain how you got the positive 1.83, or like how it switched to positive?
Yeah. So how I got the positive 1.83? It was literally. Let me find a spot here. Right here, maybe. So really, it's really just from this part here. We had basically the natural log of 0.14 equals the natural log of 0.88 and the rest of it, right? So mathematically, really what you're doing is we're just going to subtract this whole thing to the other side. And basically when we subtract this to the other side, you got your natural log of 0.14 minus the natural log of 0.88. So on your calculator, if you hit the natural log of 0.14, hit equals, and subtract it from the natural log of 0.88, that's where that number should come from.
Okay.
And it should be, it is negative though. It is a negative number. And the way it became a positive number here is when we divided to the other side this negative. So we had a negative on the bottom and a negative on top.
Mm-hmm.
They cancel each other out when we divided it. And that's how ultimately the number became positive at the end. But you will get a negative 1.83 when you do that. And then it becomes positive when we divided the minus 2.8 to the other side.
Okay, thank you.
You're welcome. I heard two people. Was that the same question or?
Yeah. How do you know like that the 0.88 goes on the inside of like on the first A, and then the 0.14 goes on the outside?
Yeah, basically when you look at the original sort of formula here, it's the right color. This guy right here, where's the A and with the little circle on the bottom, which is sometimes referred to as A naught, that's basically your initial concentration. So here is saying that the concentration basically started at 0.88 and went down to 0.14. So the 0.88 would be your initial, while this guy over here you could kind of think of as your final concentration.
Okay, that makes sense. Thank you.
And then that's obviously where we ended up at 0.14. So usually in most cases, smaller numbers out here in terms of concentration and larger number here, but technically it's kind of like your initial and your final concentrations on that. Other questions?
I see there's like the temperature included, so we don't need to pay attention.
Yeah,
to
really
that.
not needed. Not really needed here in pretty much any of these sort of kinetic equations here in terms of first order, second order, and zero order, which we'll talk about. We will see an equation a little bit later on, which is a temperature-based sort of equation in terms of kinetics, which affects the rate of the reaction. So that's where you'll need temperature. here just kind of a useless piece of information in this particular type of problem.
Okay, for sure. Thank you.
There will be some formulas that will involve temperature, and you'll need them, but here you don't really need it. It's really just a information to tell you at what temperature it was run. Again, temperature overall will have an effect, obviously, on how fast the reaction will take place, but in this particular case, you don't have to worry about it. Other questions on that? And again, a reminder that the T here is time and not temperature. So sometimes people always have T in their head as temperature. So definitely in kinetics, T for the most part, time. Other questions on any of that there? Okay. So we sort of talked about the half-life equation. Again, specifically the half-life equation for a first order reaction, and it is different for different orders, is that natural log of 2 over K. And again, that is the 0.693 over K, and that is what the natural log of 2 equals. So again, you'll sometimes see it both ways. And as I mentioned before, a number of problems will require you to use both of these sort of formulas together. And typically what will happen in a situation like that, for example, let's say they gave you like the final concentration, they gave you the initial concentration, and they want you to solve for something, say like time. And they don't actually give you the rate constant, but what they'll sometimes give you is like the half-life of it is a number. So they will sometimes just give you the half-life equation. And sometimes you need to use the half-life equation to solve for K so that you then could go back into this equation and use it. So if you ever come across a situation where like you feel like you have almost everything, but you're kind of missing, you know, 2 things out of that equation, that natural log of A equals natural log of A naught minus KT, you may have to use the half-life equation. And again, in that case, they typically will give you the value of the half-life, and then you kind of use it together. So it happens a lot, I would say. We'll see it a lot as well a little bit later on in the semester when we talk about nuclear chemistry. All radioactive decay follows first order kinetics, and that happens a lot where you do have to use kind of both of those formulas together. And it does happen in regular kinetics as well. So sometimes a half-life equation and the integrated rate law is oftentimes needed to be used together. And the half-life basically means what it sounds like. It is the time it takes for half of whatever you started with basically to go away. And that means that, you know, if you started with 10, after the first half-life, you'd have 5. After the next one, you have 2.5, and so forth. And again, it's just that time. Usually about 10 half-lives or so, you'll probably be out whatever you started with. It's almost 100% at that point. So why don't you try the bottom one there? What is the half-life of the N2O5 that decomposes with the rate constant of 5.7 times 10 to the minus 1?
Sorry, I have a question.
Yeah.
I didn't catch it, but you said something about we would use the half-life equation if we're missing like certain
Yeah, so sometimes it happens, and again, like I said, it will probably happen a little bit later on in the semester, a little bit more when we get to the nuclear chemistry part. But sometimes you have sort of a kinetics problem, and when you look at, say, this equation here, you're like, okay, I'm given like the final concentration, I got the initial concentration, I'm looking for something like time, but I'm not given the rate in the actual problem. And in that problem, instead of the rate constant given to me, they give me something like the half-life of the reaction. And then you would need to use the half-life equation to solve for the rate constant, and then plug it into the integrated rate law to solve for time. So sometimes you need to use, a lot of times, the half-life equation to figure out the rate constant because they give you that information in the problem. And then you can then use the rate constant with all the other information to solve for what you're really looking for. So that's a very common sort of thing that happens in sort of kinetic problems.
Oh, okay. Okay, thank you.
You're welcome. Okay, so here we're looking for the half-life of this, and it decomposes at a rate constant of 5.7 times 10 to the minus 4. So again, our half-life here for our first order would be the natural log of 2 over k. So we're just going to take the natural log of 2 and divide it by 5.7 times 10 to the minus 4 reciprocal seconds. And a reminder, you want to make sure that you are using your exponent button on your calculator. Otherwise, you will find yourself off on a lot of these calculations. So again, that's that EE button and so forth. And it looks like we end up with something like 1,216 seconds, which if we wanted minutes would be something like 20 minutes. And, you know, if you wanted real sig fig, since this is the only number here, this guy probably should have been something like 1,200 seconds in that particular case. So the second part of the question is, how do we know it is the first order? And we know because the units that we see associated with the rate constant is reciprocal seconds. So 1 over seconds tells us it is the first order reaction. And it also tells us then that this is the half-life equation that we should use. So again, very, very common that just the rate constant is given to you with the units, and you need to determine, you know, what order it is, and that's how you do it in this particular case. Question on that one there. And again, in a second here, we will have some more equations for different orders, and that's why, again, it's really important to understand, you know, that the units associated with the rate constant, what they mean. Any questions on that? Okay. And again, here's just sort of a graphical representation of sort of what's happening in terms of half-life. As you can see, if you count the dots there at the beginning all the way up here, after we hit that first half-life, we got half as many circles. And again, after the next one, half as many, and the next one is half as many circles. So again, it is pretty gradual decrease with time with our first order here. Okay, so why don't you try this one here and see what you come up with, and we'll talk about it. Okay, so let's take a look at this particular one here. Again, they details its first order. If we didn't know that, again, we are given the rate constant, so we can look at the units associated with it and know that it is first order. And here, again, our K is 2.9 times 10 to the minus 4 reciprocal seconds. Again, those units helping us determine that it is first order, which means we should use that integrated rate law there. In this particular case, they're nice enough to label these things. So our initial and our final. And we also have our time. So we have this guy, we have this, and we have this. So we can just plug it in. So the natural log of A would equal our initial concentration, which in this case was 0.0225. Minus our K value, which was also given to us 2.9 times 10 to the minus 4 reciprocal seconds. And our time was actually 865 seconds. So before we continue on sort of solving this one, also a good point to remind you is here and units. Very common in kinetics problems, your rate constant and your time will actually be in different units. It is not in this particular case, but it is very common that that does happen. So you do want to watch out for that as you're kind of doing these problems. Sometimes, for example, your rate constant may be in seconds and maybe your time's in minutes. It could be days and like weeks or something like that. So a lot of times those two units are not necessarily the same, and we're talking about basically the unit of time, and it does require sometimes a conversion to be done. So what we got going on is we pretty much could clean up everything on the right-hand side of the equal sign there. So again, to do that, I personally am going to take the natural log of 0.0225. I'm going to hit equals. I'm going to hit minus button. I'm going to open a parentheses and go 2.9, my exponent button, my negative button, and 4. And I'm going to times it by 865, close the parentheses, and that's going to give me a natural log of A is equal to minus 4.04508997. Don't feel like rounding right now. At this point, we do need to solve for A because we're looking for what the final concentration really is at this point. To get rid of the natural log on the left-hand side, we need to take the E on both sides. So we're going to take the E on that side. We're going to put this entire thing into there. What happens on this side when you take the E on your calculator is the natural log goes away and you end up with A. And what happens here is you should get a number. So if you do that, E again to the negative 4.04 or 4.05, if you do a little bit of rounding, you will end up with 0.01, and we'll go with 75 molar here. Any questions on that there? So again, to get rid of the natural log, we're going to take the E of both sides. And again, that's what you end up with there. We do see that the concentration did go down, which is good. If we did this by some chance and the concentration went up, that's probably not right, right? So the concentration should be going down, and it did in this particular case. Any questions on any of that math there?
As far as sig figs, is it just going to be the same as the initial concentration?
Yeah, probably for the most part for us. Kind of look around at everything here. We've got like 3 sig figs going on everybody. So probably that's ultimately what you would end up with in most cases, because technically, even though we're doing some subtraction, for example, here, technically, you know, I guess this is kind of subtraction, but really, as I mentioned earlier, also if you divide out that natural log, it's really division. So really the most of what you're kind of doing around here is division and multiplication, which means you're looking at sig figs. And in this particular case, it looks like everybody was kind of at 3 sig figs. So probably 3 sig figs would be most appropriate here.
Okay.
I'm not able to get that number. It keeps saying I have an error.
Okay, on which part, when you do the E part or the,
Yes, so the E part.
okay.
That's most likely because you're putting in a negative e. You would need to put it over 1. So it'd be 1 over e to the positive 4.045.
Okay, thank you.
Yeah, on my calculator, I could just put the E to the negative 4.04 and it comes out okay. So when I hit my calculator, it pops up an E. And double check what it pops up there. It comes up that E, I believe. Go. Oops. Pops up the E, and I personally open a parentheses and do a negative 4.04 and all the rest of the numbers. I close the parentheses and then I hit equals, and it does come to this number. Again, depending on maybe your calculator, and it might just be sometimes on calculators you need to put some parentheses around some of the numbers when you do that. Sometimes that helps. It just kind of depends on your calculator's program sometimes in terms of how you get it. Other questions? Okay. So why don't you try this one here? We're looking for what is the half-life of this reaction? Okay, so on this one, we're just looking for the half-life. So we got the rate constant given to us. And again, if they did not mention what order, that right there is going to tell us that it is first order. And again, we want to make sure that we use the first order half-life equation. And we will see very shortly here some other ones for different orders. And in this case, since we do have just the K given to us, we just want to plug it in there. And natural log of 2 divided by 0.271 reciprocal seconds. And looks like we will get something like 2.56, and the units will become seconds. So when we do the division, seconds come up on top, and we will end up with something like 2.56 seconds. It's pretty quick. Every 2.56 seconds, we're losing half of what we started with, and that's a pretty fast half-life. Again, on a lot of these things, there's a lot to punch into your calculators. I highly recommend that you do not punch too much in at once, and that's usually where a lot of people sometimes have trouble. They have trouble in two places. Either they're really not using their exponent button. So remember, I think we talked about it, you know, if you had something like 2.5 times 10 to the minus 4 in your calculator, you would hit 2.5 and you would want to use your exponent button. And again, for the negative, you want to use your negative button, looks like that, or this, and then 4. You should not be using anything when you're punching something in scientific notation, should not be using your multiplication button, should not be using like your shift and log button or any of those type of things. You shouldn't be doing any of those things. When you're just simply punching a number in scientific notation, you want to make sure that you do use your exponent button. Otherwise, you will find yourself off, especially when you start doing some things like we're doing here, natural logs, the E, all that kind of stuff, you know, you're going to find yourself off. So you want to make sure always use that exponent button and stuff like that. Again, when you do that, it should punch a 2.5. When you hit the exponent button, a lot of calculators put the E. That represents the times 10 part of the number. So that's why you don't need to do the multiplication or the 10 or anything like that. And again, it'll go -4. Or on your calculator may go like this, pop up a 0, and -4 looks something like that. So definitely make sure you use that exponent button. And the second thing that people run into trouble with is, as I was mentioning, they try to put way too much into their calculator all at once. And if you really don't do it correctly with parentheses and stuff like that correctly, you will get the wrong answer. So I highly recommend to people that kind of do a calculation, hit equals, you know, do the next calculation, hit equals. You usually will find yourself, if you keep kind of hitting equals after each mathematical step, you know, you usually will end up with the right answer. And that's usually where people sort of have some trouble. All right, so that is first order. Let us now talk about another type of reaction, which is a second order reaction, and some of the key parts of that guy as well. Pop all that stuff up. All right, so a second order reaction is one where we have a rate law as we see up here on top, where obviously the order here for A is 2, which means overall this is a second order reaction. And again, this is one way in which you could get it, where you have one reactant whose concentration squared determines the rate of the reaction. You could also get to a second order reaction by having 2 reactants. It goes to products, where the rate law would be something like K times A times B, where each of these guys would be first order, giving you a second order overall. And in that particular case, as you can see from the rate law, the rate is determined by both concentrations, right? So both concentrations have an effect on the rate. The squaring of the A concentration here has an effect on the rate when we have just one reactant. So again, there's a couple of ways that you actually get to a second order reaction. One where you have 2 reactants, or one where you have 1 reactant. In the case of 1 reactant, the square of its concentration has an effect on the rate. In the case of 2 reactants, kind of their individual concentrations will have an effect on it. Now, when we sort of rearrange and solve for the K here, which is what we're doing here, and we just look at the units, we get the typical units that are associated with a second order reaction in terms of the rate constant. And you can see they are different than first order. This is 1 over molar seconds. And just like in first order, the seconds part here doesn't always have to be seconds. It can be any unit of time. So it could be something like 1 over molar minutes, 1 over molar hours. But again, very common seconds in terms of time, as we've been talking about, is sort of a common unit of it. So again, just like we saw in these last couple of examples where the K had the units of 1 over seconds, and that told us it was first order. If you see a K value with 1 over molar seconds or molar unit of time, that will tell you that you're dealing with a second order reaction. And just like a first order reaction, a second order reaction has sort of an integrated rate law, or a concentration time dependent equation. And this is 1 over A, which is the same A, so that's like our final concentration, equals 1 over A naught, which is our initial concentration. K is our rate constant, and T here again is time. So all these guys are the same as it was in the first order, just a different concentration time equation that goes with it. And it also has a different half-life equation for a second order, which is 1 over K times the initial concentration. And unlike first order, where it was the natural log of 2 over K, the half-life of a second order is affected by the concentration, or the initial concentration of the reactant. So the initial concentration of the reactant will have an effect on the half-life. And again, if you just think about it mathematically, 1 over the initial concentration essentially, The larger the initial concentration, the smaller the half-life. The smaller the initial concentration, the larger the half-life. If you just think about it mathematically speaking, take 1 divided by, you know, a bigger number, it's going to give you a smaller number, right? And 1 divided by a smaller number gives you a bigger number. So that will have an effect. Just like what we did with the first order, we could rearrange this equation here and rearrange it as 1 over A is equal to KT plus 1 over A naught. And this is rearranging this equation in the form of a straight line. And that would give us our y is equal to mx plus b in this particular case. And that's where we get our graph for a second order. As you can see on the y, it is 1 over a. And on the x, it is t. And since this is the formula for a straight line, as you can see, it does give you a straight line. It gives you a different straight line than what we saw with our first order. First order had a negative slope. This one has a positive slope. And that's why we also see that when we take the slope of this line, it does not equal negative k. It actually just equals the rate constant in this case. Again, because the line itself will have a positive slope, and that will give you the rate constant. So same sort of things that you need to kind of know from for this slide here. You definitely need to know second order units associated with the rate constant. You need to know the time and concentration formula for second order, the half-life equation, and the proper graph that goes with a second order one as well. Any questions on that there? Okay. So again, this is a reaction, and a typical type reaction that we see, again, we commonly see, as we talked about, reactions that involve perhaps 1 reactant, 2 reactants. So again, these are common ways that reactions can come together. And what first order, second order, and as we'll talk about here, 0 order in a second. Again, what it kind of tells you is have the concentration of those reactants, how they sort of affect the overall rate. So in this particular case, if we had just 1 reactant, the square of its concentration would have an effect on the rate. And if we had 2 reactants, each of their individual concentrations, again, would have an effect. And you don't want to overcomplicate it. You could just mathematically think about these things, right? You know, if this is sort of the relationship here, you could throw in numbers. Like if you threw in 100 and if you threw in like 2, you would get obviously different values here. And you can see how that would affect, you know, the rate. Does it go up by a factor of 10? Does it go down by a factor of 10? You know, depending on how you sort of affect the concentration. Any questions on that? All right, the last sort of type of reaction that's common that we will talk about here in terms of sort of rates and integrated rate laws is a 0 order reaction. And in a 0 order reaction, we'll talk about our important stuff off of this slide as well. In a 0 order reaction, we would have a rate law where the rate would equal K times A to the 0. And I think we talked about something this the other day. When you take something to the 0, it equals 1, right? So basically this goes away. And that means that the rate for this particular reaction is equal to the rate constant. And since this is equal to 1, it will have units of molarity over seconds, the same units that you see for the rate. And again, this is how you could recognize that you are talking about a 0 order reaction overall. If you're given the rate constant and it has units of molarity over seconds. And again, as we've been talking about in terms of the time part of it, doesn't always have to be seconds, but some unit of time. Now, what this tells us when we look at the rate is equal to K times A to the 0 are really just equal to K. What this tells us in this particular type of reaction, the rate of the reaction is independent of the concentration, right? There's no concentration. So since really the rate law here is the rate is equal to K, you can do whatever you like with the concentration of the reactants here. It should technically have no effect on the rate of the reaction. Again, as you can see, it's not in the rate law, the concentration. So the concentration and the rate here are independent of each other. They'll have no effect on each other. Again, different than what we saw for first order, where the concentration would have an effect if you kind of raised it or lowered it in terms of the rate of the reaction. Also for second order, if you raise or lower the concentration of the reactants, it would have an effect here. This would have no effect. It's sort of independent of it. We also have a concentration time dependent one, or integrated rate law as well, and that is A is equal to A naught minus KT, and that looks almost like the first order one, except that there's no natural log in it. So there's no natural log happening there. And our half-life equation for a zero order is the initial concentration divided by 2K, and much like a second order, the half-life is affected by the initial concentration of A in this particular case. And in this case, the A is actually on top. So again, if you increase the concentration of A, we're going to get a larger value for the half-life. And if you decrease, it'll become a smaller value, again, because it's on top of the fraction there. So it'll have that effect on it. Now, you may ask yourself, well, maybe I might not be able to remember, the half-life equations and stuff like that. So if you're not terribly bad at sort of math, you could actually use this equation here, and you can solve for T, because what we mean when we have the half-life equation is the initial concentration divided by 2. So if you kind of substitute that into here and solve for T, and you do it correctly, it will get you down to this guy. So you can use any of these sort of integrated rate laws and put basically an initial concentration divided by 2 in for the final, and solve for T, and you will actually get the half-life equation. Again, if you do the math correctly, probably easier just to remember it, to be honest with you. We could also rearrange this integrated rate law here, kind of similar to what we've done with the others. It would be A is equal to minus KT plus A naught. And again, this is it written in the form of a straight line, y equals mx plus b. And again, this is where we get our graph. So on the y is A, on the x is t, like everybody else. And again, this yields us a straight line, just like the others. And because we do have a negative slope here, the slope is equal to negative k. So again, that negative and negative value will turn your k value into a positive value. And again, that's why it's not equal to just k, but it's equal to negative k, because the slope itself of that line will be negative, and it will turn it in there. So kind of our same deal here in terms of what you need to know for zero order units. Going to help you out, because not going to in every problem screaming in lights what order it is. The rate law there for concentration and time, our half-life equation, and this graph. Now, speaking of this graph, you may look at this graph and go, this is the concentration versus time. And I seem to remember that from earlier, and you would be correct if we flow back here. Oops, there it is. And if we flow back here, that is the same graph that we have here for first order, concentration versus time. The difference is when you look at those two graphs, for a first order graph like we see here, it is not a linear line. It is decreasing with time. So when you do concentration versus time, and you do not get a linear graph, but you get this kind of decreasing with time graph, it is probably a first order reaction. If you do that same graph like we see here on the very last slide, where you graph the concentration versus time, and you do get a linear line like we see here on this slide, comes in, then it is zero order. So like I said, for the first order, typically they don't usually use this graph, because usually they like to do linear graphs, but sometimes they will still do it. But the difference between this concentration versus time and the first order concentration versus time is that the zero order will give us a linear graph, while our first order will not give us a linear graph. Any questions on that part of it there? All right, so why don't you try an example here, see what you come up with. The reaction is second order. We got initial concentration of Q, and after 5 times 10 to the 2 seconds, find the rate constant. So take a couple minutes and we'll talk about it. Okay, so let's see. So they do tell us the second order, which if they didn't, you would have no idea, because we are looking for the rate constant in this case, so you don't have the units there to determine that. But definitely because it's first order here, so that should automatically tell you you want to be using the second order one, because it's second order, I think I said that. And it would be this guy here, 1 array equals 1 array naught plus KT. And in this particular case, we do have the initial, so we have this one. We do have the rate, we have the time, and we do have our final concentration. So we can solve for K in this case. So we just want to plug it in. So it's going to be 1 over our final, which is again the 0.001. And that's going to equal 1 over our initial, which is 0.01. And that's going to be plus K, which is what we're looking for. And that's like 500 seconds, right? So again, mathematically here, personally, what I would do is I would take 1 divided by 0.001 and hit equals. And then I would subtract to the other side 1 divided by 0.01. So again, I'm basically taking this to the other side and subtracting it. So I'm doing 1 over 0.001 minus 1 over 0.01 equals K times 500. And again, if you do all that good stuff there, that's going to give you 900, I believe. And that's going to equal K times 500. So we're going to divide it by 500. And that's going to give us 1.8. Now, you may be wondering about the units. I didn't really put it here, but this technically is molarity, and molarity, which technically means the units here is 1 over molarity for the 900. So when I divide that S to the other side, I end up with 1 over molar seconds, which is good because, again, that is the typical units that are associated with a second order reaction. Any questions on that step there? So again, sometimes people have a struggle with kind of punching into their calculators correctly. I find that the simpler you do it, kind of one step at a time, and don't be afraid to use the equals button along the way, makes a big difference in terms of getting the right answer versus trying to punch everything in at once. Again, a very common place where people kind of error. Any questions on first order, second order, zero order? Again, you do need to know those equations, the half-life equations. You do need to know the units associated with the rate constant, and you do need to know the graphs associated with it as well. Questions on any of that stuff there? And obviously be able to solve for pretty much anything there. K, time, concentration, initial, final concentrations. Any questions on any of that there? And here's just a nice little summary table, pretty much what you kind of need to know for those different ones. Again, the different orders, the concentration time equation, again, sometimes called the integrated rate laws, and the half-life equations for each of those. Again, you can see that they are different depending on the orders, and that's why it's really critical that if they don't tell you the order of the reaction, you're able to recognize those units associated with the rate constant, so you get everything correct there. And lastly as well, another common way, especially sort of experimentally, to try to determine the order of a reaction is literally sort of through graphs, and y equals mx plus b, the equation for a straight line. Again, doing a linear graph, a best fit graph, is something that's done a lot, especially in the kinetics experiments. And in fact, not the first one, but the second experiment, I think, second real experiment that we do, you will have to do a number of graphs, and you will have to make graphs for first order, second order, and zero order, and determine which one is most linear. And the one that's most linear will allow you to determine the overall order of the reaction for that. And when you do it sort of graphically on, say, something like Excel, you could get the R squared value. That is the linear coefficient value. The linear coefficient value is perfectly linear if you have a value of 1. And anything near 1 is perfectly linear. And that's sometimes graphically how you try to determine these things. So if you did an experiment, you would, if you weren't sure, you would take, for example, the natural log of A and versus time and make a graph. You would take A versus time and make a graph, which would represent zero order. And you would take 1 over A versus time, and that would represent second order. And what you would do is a best fit plot for each of those, do some linear regression, and figure out the R squared value, and whichever one was closest to 1 would tell you that is the most linear and what the order is. So again, understanding the graphs that are associated with these sort of straight line graphs is a very common way to sort of determine the order of a reaction. Any questions on that there? And you'll get a lot of practice on that on like the second experiment that we get to. It's a lot less graphs than you used to make in that experiment. They used to make something like maybe like 32 graphs in the old days. In addition to doing the experiment, 32 graphs plus a hand graph and stuff like that. So they cut out some of those graphs, at least it's a lot easier. It used to be, and like I said, years ago, you used to actually have to do the experiment and then make the graphs, and it was a pretty long several weeks of doing that experiment. Any questions on any of that stuff there? Okay, so we are then going to kind of transition now into talking about temperature and really sort of the effect of temperature on the rate of a reaction and different types of reactions. So let's take a look at that since we've got a couple of minutes, I think. These are two energy diagrams, and and these energy diagrams do represent two types of reactions. One is a exothermic reaction and one is a endothermic reaction. And hopefully, as you know, exothermic means that heat and energy is released. While endothermic means that heat and energy is absorbed. And you talked about that in Chem 50. And you should also know that usually when we think about energy and reactions, we usually think about delta H, which is again our enthalpy. And our enthalpy basically is the heat of a reaction. And if it's an exothermic reaction, the delta H value is typically negative. If it's an endothermic reaction, the delta H value is positive. So again, you probably did a whole bunch of stuff with enthalpy and everybody's favorite thing, Hess's laws and all that kind of great stuff. But when we look at these exothermic reaction, we see here are reactants over here. And down here are our products. And this is typically how an exothermic energy diagram looks like. What we see is our reactants are higher in energy than our products. So whenever you have your reactants that are higher in energy than your products, that is definitely an exothermic reaction. Just logically thinking about it, in order for those reactants to get down to the products, energy has to be given off. So energy has to be given off, and that is again a exothermic reaction. And that is opposite of what we see on our endothermic. In our endothermic reaction, our reactants are lower in energy than our products. And that usually is a pretty good sign that you're dealing with an endothermic reaction. And again, logically speaking, for our reactants to get up in terms of energy to our products, energy needs to be put in or absorbed, and that gives you your endothermic process. Now, as a reaction basically progresses from reactants to products, as you can see here in this graph and the other graph, there is actually a hill that the reactants has to climb basically to get to the other side. And that is what is known as E of A, and that is the activation energy. So the activation energy is really that hill that the reactants has to climb to get to the other side to form products. It is also really known as the minimum amount of energy required for a chemical reaction to take place. Not all reactions take place even if people collide with each other. In order for a reaction to take place, really two things have to happen. They do need to come in contact with each other, but they do have to come in contact with each other in sort of the right location with the right amount. Whoa, I just lost like the whole background there. That was freaky. It does come together with each other in the right location, and that's sort of that active spot, and it needs to have the minimum amount of energy for a reaction to occur. And basically what that is the hill that it has to climb, that activation energy. So not all collisions will always result in an actual reaction happening if those two things are not met. And we see our hill over here for our endothermic reaction is here. And we do see in comparison, the one that has the greater activation energy is the endothermic, right? Which makes sense because you have to put energy in to do that. And it takes a little bit bigger of a hill to get to the other side. So what that means in terms of the rate is you could imagine that if the hill is smaller, a greater amount of reactants would be able to get to the other side. While if the hill is bigger, like it is over here on our endothermic, it's going to take longer for everybody to get up and over the other side. Just like if you were walking a hill, if you had a big giant hill in front of you, it's probably going to take you longer to get up and over the hill than it would if you had a much smaller hill if you were walking there. And it does affect the rate of the reaction, that sort of activation energy or that energy barrier. When we do get to the very top of the hill, this is what is sometimes referred to as the transition state. And the transition state is basically the highest point there in terms of energy. And basically what we have going on there, which is this little guy with a kind of a weird symbol there, kind of looks like this type of symbol. And what that represents is this is what is sometimes referred to as a transition state complex. Or an activated complex is sometimes called. And what you have there is something where you have a guy that is, if you just think about what's happening in a reaction, as they go from reactants, all the bonds need to break. And as they move from reactants to products, you need to make some more new bonds need to be formed. So at the very peak there, where you have that transition state complex or that activated complex, you have a species that has partially broken bonds, and you have somebody that has partially made bonds. So you got this sort of intermediate, if you will, where it's starting to break a lot of those bonds and then starting to make some new bonds at the same time. And one thing that you should also know in terms of energy is when we are in higher states of energy, we're not very stable, right? Things don't really like to be in really high states of energy. They like to be in the lowest state of energy that's possible. So typically speaking, what happens when we get to the top of the hill is rather quickly it will kind of drop to the other side because this is really a pretty unstable complex. And if you think about it, that's pretty much the peak in terms of energy where that is at the top of the hill. And that's why, you know, it's usually very hard sometimes in reactions to isolate that intermediate, that activated complex, because it's so high in energy. It's got these partially made bonds, partially broken bonds that it really doesn't like to hang around a super long time, and it will kind of quickly go off into product formation. So in a lot of reactions, it's very hard to sort of isolate that little guy because, you know, it happens very, very quickly. So the activation energy, which is that minimum energy to go from one side to the next in terms of reactants to products, obviously the greater that hill, the slower the reaction is going to occur. It's going to take a lot more energy to get up and over. You're going to have less proportion of molecules that do have that energy to get up and over to the other side. While if you have a smaller hill to climb, you know, things can go over a lot quicker to the other side, usually results in a faster rate. Any questions on that so far? It's probably a good place to stop, I think. So we'll take a break here. 11:30, we will have some lab. It is lab report and data analysis experiment. It is actually in your lab notebook. So again, the lab notebook is up there on Canvas. So it actually is an experiment in there. And again, it will walk you through making some graphs, you know, and kind of incorporating them into Word and stuff like that. And we'll talk a little bit about that. And in addition, we'll talk about the formal lab reports that you'll have to write and sort of what that entails. All right, so we'll stop there. I'll see everybody in about 20 minutes coming through the lab link. Make sure you type here in the chat box if you didn't do so when you got here. And I'll see everybody in about 20.